let's do some other convolution examples. So let's consider that. Well, let's take some simple indicator of some simple rectangular function. Phi of x is the indicator of -1/2, 1/2, okay, of x. And let's talk about this h function, which is going to be an infinite function, which is called by the guy who invented it or qualified it, is the Heaviside. That's the name of one mathematician. Heaviside function, okay, or it's also called the step function. What does it look like? It just looks like a giant step, okay, right? So that's going to be the function that is equal to h of x is equal to 1 if x is greater or equal to 0 and the 0 otherwise. Okay, well, we can choose it to have the fixed value of 1 and 0 or the contrary, but let's say we take this one. And I want us to compute, so obviously h belongs to L infinite, not to L1, because it has a constant value on an infinite domain, and whereas phi belongs to L1. Okay, indeed, because it's just the nice rectangular function like this. Okay, that's -1/2, 1/2, and that's one. Okay, let's do the convolution of the two together. Phi convolved with h. Of course, one is in L1, the other one is in L infinite, so you know that that belongs to L infinite, and even it's continuous. That should be C0 of R, right? So let's compute that. So that should be an R, sorry. Okay. So let's write phi convolved with h of x is going to be the integral on R of indicator of -1/2, 1/2 of, maybe let's choose that x minus y times the indicator of y from 0 plus infinity dy. I think it's going to be easier if I swap the rules of phi and h, meaning if I write it this way, -1/2, 1/2 of y times this one, x minus y of 0 plus infinity. Why is that going to be, seems easier? It's just because then I can reduce the interval of integration to a finite one instead of an infinite one. Okay, so basically that makes it much easier. X minus y on 0 plus infinity. Okay, and that is dy. Right, so let's see what we can do. So we've got the integral of that indicator function. So we would like to maybe reduce things again. Okay, so let's see. That what do we have? We have that y is between -1/2 and 1/2. And I also need x plus y to be greater than 0. Okay, from the indicator function from that one. Okay, that's what it indicates me. The first inequality just comes from the integration interval. Okay, so let's see what we can do with those two inequalities. So I've got, on one hand, let's write it this way, y, oh sorry, that was a minus, x minus y. Y is supposed to be smaller than x, and y is supposed to be between -1/2 and 1/2. So depending on where the x is with respect to the values -1/2 and 1/2, we're going to have some very different values. Okay, so let's assume, so you see, first thing, if x is smaller than -1/2. So our indicator function, that one on 0 plus infinity, that's our Heaviside function, applied to 1 minus x, is going to be equal to 0 if x minus y is smaller or strictly smaller than 0. Okay, so it's going to be 0 if x is smaller than y, right? But in our case, we really want that y is bigger than -1/2. Okay, so if x is smaller than 1/2 and -1/2 and y is bigger than this value, then this heaviside function for these values of so x minus y is going to be equal to 0. Okay, so if x is smaller or equal to -1/2, then the convolution of phi with h is equal to 0. Okay, next we will have, maybe it's easier to consider directly the case when x is bigger than 1/2, right? So x is bigger than 1/2. We have that y is between -1/2 and 1/2, and so which is more or equal to x. So that's fine. Our indicator function for all x bigger than 1/2 of x minus y of 0 plus infinity is going to be equal to 1. Okay, that's always going to happen when y is between -1/2 and 1/2 and x itself is bigger than 1/2. So our convolution is going to be given by the integral of -1/2 of the one function. Okay, which is just so dy. So that's just going to be integral of y, -1/2 that's equal to 1. Okay, so it's a constant equal to 1 when our function is, our x is strictly bigger than 1. And now let's look at the third case when x is between -1/2, 1/2, and y is also smaller, should be smaller than x, which itself is smaller than 1/2, so that's okay for y, and bigger than 1/2, so that still works. We can still have some y's between -1/2 and x. And so what are we going to say? We just have phi convolved with h of x is going to be the integral between -1/2 and x of the one function dy. Okay, and so that's just going to be y between x and -1/2, so that's x plus 1/2. Okay, so what do we get? The convolution of phi with h has those three pieces. If x is smaller than -1/2, it's going to be 0. If x is bigger than 1/2, it's going to be 1. And if x is in between, so that's going to be x plus 1/2 if x belongs to -1/2, 1/2. I should probably exclude some pieces here. Okay, so what did we have? Let's look at that. The original functions that we wanted to convolve, we had that heaviside function. So that's h of x. We had this phi function. The scale is not very nice. 1/2, that's 1. So, and 0 otherwise, so that's phi. And what we obtain is that, let me pick a nice color, let's check the orange. So if it's smaller than 0, it's going to be 0, or maybe I should do it like this. All right, it's going to be 0 here, it's going to be 1 here, and in between it's just going to blend the two functions. It's going to give you that one. All right, so that's the convolution is in that green one. Okay, so you will have to deal with this kind of examples where you have to see what it makes to take the indicator of something that is mixing the two variables. So that's maybe one non-trivial part that we really have to be rigorous with. Okay,